Hello, good day. Yes, is this Louise Plumbers Association?
Yeah, girl, so it's Uwan's late or early. Oh wait, hold on, there's somebody calling her. Hi, good day. This is UB Plumbers Association. How may I assist you?
Oh, hi. Right now I'm calling to complain about the pressure issue in the bathrooms here in FST engineering. What's been happening is like there's poor water pressure and like for the past few weeks like they're calling and complaining and nobody has fixed it here. What I'd like is for you to come and fix it and tell me what's the problem.
Okay, I'm sorry to hear about the problem. We'll see to get it fixed as soon as possible.
Alright, so can you meet me for 1 p.m.?
What about tomorrow instead?
No. Tomorrow is not a good day and you need to meet me for 1.
Alright then, sir. 1 is fine, but can you meet me here instead?
Oh, you want me to meet you? Alright, where?
Physics department, FST, 4th floor, meet me there.
Alright, I'll come.
Hi, my name is Ankit. How can I help you?
Sorry, we had a guy coming to fix me, right?
Yeah, sure.
Alright, well, for the past couple of weeks, it has an issue with my pipe. The water pressure is too low. I'm not sure where you need to come and fix it.
Okay. Do you have specs of the pipe or a picture I could see?
Oh, yeah.
Okay. Well, clearly the size of that pipe is too big. That's why you're having low pressure.
What does the size of the pipe have to do with the water pressure?
Well, we at UB Plumbers Association can explain that for you. Hi, my name is Raquel, and today I will discuss fluids in motion. But before we can really discuss fluids in motion, firstly, we want to ask ourselves, what is a fluid? Well, according to the Fundamental of Physics by Resnick, Halliday, and Walker, a fluid, when compared to a solid, is a substance that flows. So, fluids are basically gases and liquids, and they conform to the shape of the container that they are placed in because they cannot sustain net forces that is tangential to their surface. So, firstly, we'll be discussing real fluids, then move on to ideal fluids. So, in a real fluid, there are frictional forces. These frictional forces are from the walls of the pipe itself and within the fluid itself. This converts some of the kinetic energy within the fluid into heat, so therefore energy from within the fluid is lost. Well, the forces that cause the problem for the layers of the fluid to slip and slide past each other is called viscosity. Well, viscosity is a measure of the resistance of a fluid to the relative motion. So we can measure the viscosity of a fluid by measuring the viscous strand force between the two plates. Well, for ideal fluids, they must meet the following criteria, which is steady flow, which is a laminar flow, which means that all particles take the same path as the previous particle. Next, a rotational flow, which means that there is no angular velocity within the fluid, which means that there is no turbulence like whirlpools or eddy currents. The next point, non-viscous flow, meaning that there is no viscosity within the fluid, so no kinetic energy is converted to heat energy. Last point, incompressible flow, meaning that the density within the fluid remains the same throughout the whole passage through the pipe.
Hi, good day. I'm Ankit Das, and I'll be discussing Torricelli's theorem. So, Torricelli's theorem is a theorem named after Evangelista Torricelli in 1643, who discovered an interesting property of fluid flow from an opening in a tank. We can derive this relationship by considering fluid in a tank as well as applying Bernoulli's theorem or Bernoulli's equation. So, first, we know from Bernoulli's equation that the pressure, the kinetic energy density, and potential energy density at all points in a fluid in a tank are constant. So, if we consider these properties at the level of the hole and at the top or the surface of the fluid, we can derive the theorem. So first, let's start by noting that the pressure at the top and the pressure at the hole are the same because they are both exposed to the atmosphere. So they will just be atmospheric pressure and we can cancel them out. Next off, if we consider that the cross-sectional area of the tank is significantly greater than the area of the hole, then we can assume that the change in height of the surface of the water is negligible. So the velocity at the top, the change in distance would essentially be zero, and we can cross this term out. Next, in the remaining terms, we can cancel density of the fluid from all the terms, and we remain with this relationship. Now, if we rearrange this equation, we can make it in the form of a kinematic equation. So, from this form of the kinematic equation, Torricelli's theorem essentially states that if a drop of liquid is in free fall from the level of the surface of the liquid in the tank, then when it reaches the level of the hole, its instantaneous speed at that point would be the same as that of the effluent liquid. Now, let's see this theorem in action. As we can see from the setup, the effluent water at lower levels has higher ranges, since the speed of a drop of water in freefall would be greater at lower points in its path. Torricelli's theorem can be very useful to people such as firefighters who need high effluent speed of water to quell massive flames and save lives.
Hi, good day. My name is Darian Cupid, and today what we're going to be talking about is the continuity equation. This is denoted by Q is equal to AL on T, where Q is equal to the mass flow rate. What is that? Mass flow rate can be denoted by the concept that the mass of the particles flowing at any point in the pipe within a particular time frame will be equal at all points within the pipe. If this were true, it would be completely opposite to the concepts that my partner would have talked about just a few seconds ago. So within the equation, L on T can be denoted by velocity, which is V. Therefore, we have a secondary equation in which Q, mass flow rate, is equal to the product of area and velocity. Because of the principle of the mass flow rate, Q1 will always be equal to Q2. Therefore, A1V1 is equal to A2V2. But now to actually show this in a pipe system, for a particular portion of the pipe at x1, this position, we have an area A1 and it goes at a certain velocity V1. Suppose there are 5 particles traveling along this path. So A1 V1 would be equal to the mass flow rate at that point. Because both of them should be equal theoretically, when the water now flows at this portion, the mass flow rate accounts for this by increasing the velocity as there's a smaller area. Therefore, we can also see that if the water was going in the reverse, that for a higher velocity, the equation would account for this by decreasing its velocity for an increasing area.
Hi, good day. I am Ricardo Deola, and today we will be discussing Bernoulli's equation. Bernoulli's equation comes from Bernoulli's principle, which states that within a horizontal flow of fluid, any increase in fluid speed will result in a decrease in its pressure. It is derived from the same principle as the continuity equation, which is the conservation of energy. It is basically the same equation, but with added height and density of the fluid, as they have an effect on the energy level within the fluid. Bernoulli's equation states that P plus rho gy plus half rho v squared remains constant, which basically means that energy due to pressure plus potential energy density plus kinetic energy density would remain constant. Where we see a change in the diameter of the pipe, where the initial velocity is lower than the final velocity, meanwhile the initial pressure is much higher than the final pressure, and therefore energy is consumed.
Now do you understand why a smaller pipe is needed?
Yeah, I think so. I was trying to follow it.
Cool.